Hi everyone, it's Mrs. Griffin with the Unit 8 Lesson 6 video where we're going to start talking about proofs that use circle properties. So to begin with, please try the opening exercise. Pause now. And the answer should be 44. Okay, so some of the proof blocks that we will be using are the same properties we were talking about in our notes. All radii of a circle are congruent, radii of congruent circles are congruent, two circles with congruent radii are congruent. If you have congruent chords, they cut congruent arcs, and vice versa. I'm just going to write this part for all of them, regardless of which direction that we're using it. Central angles that intercept congruent arcs are congruent. Inscribed angles that intercept the same arc are congruent, or that intercept congruent arcs are congruent. Those are two different proof blocks, one or the other. Parallel lines cut congruent arcs. An inscribed angle in a semicircle is a right angle. A triangle inscribed in a semicircle is a right triangle. These two can also be called Thales' theorem. A radius or diameter that's perpendicular to a chord bisects the chord and its arcs. A radius or diameter that bisects a chord also bisects the arcs cut by that chord and is perpendicular to that chord. These three are all different properties. You can use just whatever 2 out of 3 you happen to be needing for the particular proof we're doing. So on to some examples. Okay, so for example 1, we have a whole lot of information given, but what it all boils down to is that really what we just have is circle O. And so our given is circle O. And you can describe more if you'd like. It says that chords AD and CB are drawn, but nothing more. They want us to prove that AE times EB equals CE times ED. Remember, anytime you see multiplication in your proof, that means you're going to be doing an angle-angle similarity proof. So we need to find angle-angles. So the first thing we're going to look at is I'm noticing that I have inscribed angles all over the place. I'm seeing that angle A is inscribed to arc DB and angle C is also inscribed to arc DB. And so if they're inscribed to the same arc, they have to be congruent to one another. I'm seeing the same thing happen with angle D being inscribed to AC and angle B also being inscribed to AC. And so if they're inscribed to the same arc, they have to be congruent as well. And so the property that says that is that inscribed angles of the same arc are congruent. So what we're going to do is we're going to write that two different things happen. We had angle A congruent to angle C, and we had angle D congruent to angle B. And since both of those are happening, I'm going to do 2 outputs on that. And now I have both of my angles for angle-angle. So I can say that my triangles are similar now by angle-angle similarity. So triangle ADE is going to be similar to triangle CBE. Okay, now the thing that always comes after that is if we have similar triangles, we're allowed to put their sides into a proportion. So corresponding sides of similar triangles are proportional. And I can take the proof statement and use it to write a proportion. Remember, it needs to cross multiply this way. So AE has to cross multiply with EB, and CE has to cross multiply with ED. And then finally, after that, the product of the means equals the product of the extremes is how we can write that AE times EB is equal to CE times ED. Now, I am going to start putting tables here because I do think it's very helpful and organized to write them that way as well. So if you look at what I did here, remember the first thing I said was that inscribed angles of the same arc are congruent, and I used those to say that A was congruent to C and B was congruent to D. The statement was the parts of the picture, the reason was the block that went before it. Next I said, okay, that means I have 2 angles for angle-angle similarity, which makes my triangle similar. And then I said, all right, after that always has to come corresponding sides of similar triangles are proportional, and I created the proportion. And then finally, the product of the means equals the product of the extremes. It's nice for those of you who really don't like doing these pathways. Okay, for number 2. We have just given the figure again, so really not much of a given for us. And again, I'm noticing multiplication, so I know I need to do an angle-angle proof. Now, I have to figure out which triangles, because there are multiple triangles in this picture. So what I need to do is go, okay, RQ is aside from one of the triangles, and RP is aside from the other one. And then RS will be from this one, and RT from this one. And so I have these two triangles, and if you want to draw them out separately to make it easier for you to see them, please do that. You are welcome to. So there's my yellow one on top and my green one on the bottom. Now, using the circle rules, I have to figure out some way to get angle-angle similarity. The first thing I notice is that they overlap, and the second thing I notice is that I have inscribed angles, and both of those inscribed angles would be half of the same arc QS. And so I'm going to say that inscribed angles of the same arc are congruent using angle P and angle T. And that's the same thing I did down here too. Inscribed angles of the same arc are congruent. And then I said, okay, I have reflexive angle R. So I'm going to use my picture and reflexive, and I'm going to say that angle R is congruent to angle R. Same thing down here. And then I have my two angle pairs that I need for AA. So I'm going to bring those into my AA block and use that to say that triangle PRS is similar to triangle TRQ. And I did the same thing here. Angle, angle makes the triangle similar. After that, just like before, is going to be my corresponding sides are proportional. Same thing here. And so I'll use that to make a proportion. Remember, it has to cross multiply the way that the proof does. So RQ has to multiply by RP, and RS has to multiply by RT. Same thing here. And then finally, I would conclude it with product of the means equals product of the extremes. And I would do the cross multiplication, and I would get my proof statement. And the same thing if I do that in a table. All right, now for number 3, you can see we're not dealing with multiplication as a proof anymore, because this isn't going to be a similar triangle proof. We're trying to prove angle STG and angle DTG are congruent. I'm just going to give myself a little mark of where those are, those two angles. Well, I notice that they're inscribed. I'm also going to notice what else is given to me. I have not just circle O, but I have something important because there's vocab here. Okay, so I have circle O, that's great, but I also have that TG bisects SD, and that's a diameter bisecting a chord. You can remember, if a diameter bisects a chord, it also bisects the arcs. So that would mean that arc SG and arc GD are going to end up congruent, because if TG bisects chord SD, then TG also bisects arc SD, and by the definition of bisector, that would make arc SG congruent to arc DG. And then these angles here are inscribed angles to those two arcs, this one to arc SG and this one to arc GD, so inscribed angles of congruent arcs are congruent, and I would get my proof. And the same thing down here. If a diameter bisects the chord, it also bisects the arc, so it bisects arc SD, and by the definition of bisector, I'd get two congruent arcs, and then my inscribed angles would be congruent. Okay, for number 4. All right, this time, we're trying to prove segment AC is congruent to segment FD, so I definitely don't want to use angle again to get congruent things. So I've got a lot happening here. I've got circle O, I've got AB is congruent to FE, and I've got BC is congruent to DE. I did split them into two givens because I did have two different congruent concepts, and I was going to use them a little differently. You can put them together here, though. The first thing I'm going to notice is if I have congruent segments, then that means the arcs outside of them have to be the same as one another as well. So, congruent chords cut congruent arcs. If chord AB is congruent to chord FE, then arc AB is congruent to arc FE. And the same thing with BC and DE. And I did that here as well. Now, I can do things with arcs that I could do with segments like add and subtract as well, because these are touching. So I can take the left-hand side of this and add those together since they connect together, and so do these. I can add congruent things to get congruent answers. So I can take AB and add on BC as an arc, as well as FE and DE as an arc. And then after addition is always substitution, where you put those together. So taking arc AB and adding to it arc BC results in arc AC. And then on the other half, taking arc FE and adding on to it arc ED results in arc FD. And I now know that arc AC and arc FD are congruent. Now go back to that first concept that we learned. And I can tell that congruent chords cut congruent arcs, but that works in both directions. So if these two arcs are congruent, then the chords that connect them, end to end, A to C, and end to end, F to D, the ones with the same names, they have to be congruent as well. So for the same exact reason, congruent chords cut congruent arcs. I'm just going the other way around. I'm using the arcs to get the chords. That would make segment AC or chord AC congruent to chord FD, which is our proof. Okay, so we've done basic things with our circle rules and we've done similar triangle proofs. Let's go back and remember a congruent triangle proof. Alright, so we are trying to prove that triangle ACD is congruent to triangle BDC. And if you want to separate them into two pictures, you can. And a whole lot of information here, but I'm basically going to use that AD is congruent to BC for starters. Now those give me a side pair for these triangles, but also keep in mind the same thing from the previous problem. Congruent chords cut congruent arcs. So if chord AD and chord BC are congruent, so are the arcs. So I can use that to say that arc AD is congruent to arc BC. And that's useful because if you look at the triangles, a lot of inscribed angles are happening. And inscribed to arc AD is right here, this angle 1. And inscribed to arc BC is right here, this angle 2. And so I'll be able to say that angle 1 and angle 2 are congruent to one another because inscribed angles of congruent arcs are congruent. And I did that same process down here. First I did congruent chords cut congruent arcs to get the arcs, and then I did inscribed angles of congruent arcs are congruent to get angles 1 and 2. Now, I can't use the reflexive here because I would have ASS if I did that, so even though it's there, I'm not going to be able to use it in this particular situation. So instead, I'm going to look at my angle here and how those are also inscribed, and both of them are going to be half of DC. So those are going to end up congruent to one another as well. And so I'm going to say that inscribed angles of the same arc are congruent off of that circle to get angle 3 congruent to angle 4. And then I'll have angle side because I have those two angles plus this side from earlier from the given. And that will give me triangle ACD congruent to triangle BDC. And then lastly, number 6. This one's a little different because we have to draw our own picture. So we have to have a circle. It says a diameter, if a diameter is perpendicular to a chord. So we're going to draw a diameter in, we're going to draw a chord in, and we're going to say the given is that they are perpendicular. I'm going to call it center O, and I'm going to name where they intersect E. Now I can't use the theorem to prove it, so I'm just going to go ahead and use the fact that perpendicular lines form congruent right angles and call these two right angles angle 1 and angle 2. Now I need to have triangles, and I can only add lines that help me, so I'm going to add in 2 radii to create triangles because I know all radii of a circle are congruent. And if they're congruent, so are these angles because OCD is an isosceles triangle. Now I can say the triangles are congruent by angle side, and use CPCTC to help me show that the chord is bisected, that CE and ED are congruent. And if they're congruent, that means that we do have a segment bisector after all. And here's the table. See you in class.